All right, so let's have a look at what you need to know for chemical equilibriums. We need to be aware that equilibrium is about talking about a closed system. So that means that we're not gaining or losing anything from the mixture, and we're talking about them being at a fixed temperature, which is also important. So we use the word dynamic, which means that it's constantly moving. And what that really means is that we're getting the same amount of reactants lost as we are products formed. So it's at a point where nothing's changing in terms of overall amount of reactants and products, but there are constant changes between the reactants and products themselves. So that's what we mean when we say dynamic. We also need to be able to talk about the position of the equilibrium. So we need to be using the Kc constant, which we'll talk about, and that this has a relationship between the concentration of the reactants and products, and we need to be able to do some calculations based on this relationship. We also need to be able to talk about the changes in concentration of reactants and products and how we can represent them graphically, so drawing and interpreting graphs. And finally, we need to be able to talk about or calculate initial concentrations of reactants or final concentrations at equilibrium, dependent on the initial concentrations, the temperature, the value of Kc, and we need to be able to talk about the relationship between all of these things and pressure as well. So let's start taking a look. Equilibrium, we have this general reaction where we're saying that A and B are our reactants and C and D are our products. And given any situation, we're talking about these being reversible. So chemicals that you've talked about before, so we've got NO2 here, and then we've got N2O2. So we can see in this reaction, at 25 degrees, both of these in equilibrium, so nothing's changing. In terms of overall amounts, remember dynamic equilibrium, so small bits are changing, but no noticeable colour change. So what this reaction is doing is it's showing that we've got these both at the same temperature, so they're balanced. If we change the temperature, so we've got one at 0 degrees and the other at 100 degrees, so we've got two beakers here of a solution, either cold or hot, and I think in this case it's water, we can see that the colour change. So a bit of a checklist of things you need to know. So no reactants are added and no products are removed at equilibrium. So like I said before, both the forwards reaction and the backwards reaction are occurring at the same time. Now this is a bit of a foreign concept to you because we're used to talking about reactions only going in one direction. But in equilibrium reactions, they occur both ways. So the forward reaction happens, but also the backward reaction happens. So when it's reached equilibrium, we're saying it's occurring at the same rate. So the amount of reactants being produced is the same as the amount of products being produced. And so it looks like it's stopped, but it's in equilibrium, so it's moving backwards and forwards at the same rate. The concentration of the reactants and products are constant, so it doesn't mean that they're exactly the same. It doesn't mean that we've hit, so if we're talking about a reaction, the reaction doesn't always stop in the middle where the products and reactants are the same. Sometimes it stops more towards the products, sometimes it stops more towards the reactants, and there's ways of us calculating that, and we'll go through that later. It's only in a closed system, so that means nothing's added or removed, and it occurs at a fixed temperature, and we see this equilibrium symbol, and it often more looks like this. So we see these double arrows. Alright, so let's take this reaction here, where we have a colourless hydrogen gas and a purple iodine gas, and they react together to form a colourless hydrogen iodine. So the constant colour indicates that it's at equilibrium. Now that could be a pale purple, depending on how much of the reactants and how much of the products have been formed. So if we've still got some reactants present, it's still going to have some tinge of purple. More reactants, it'll be a darker purple. And more products, it's going to be a lighter purple. Alright, so when we're writing this out, we use these square brackets to mean concentration. And you've seen this before when we've talked about the concentration of protons present. So you've seen that. We can write the Kc value. So Kc, in this case, we can see it here, is the concentration of the products, so Hi. But the important part is we also need to consider the number in front. So if there's a number in front, so in this case the number of moles is 2, so we put it to the power of 2, divide by the concentration of the reactants. So H2 times by I2. Now, because the number of moles in front of both of these is 1, we don't need to write a power. We could write to the power of 1, but it doesn't make any sense to do that, so we leave it as is. So the size of Kc is important. If we get a Kc value that is really small, so a lot less than 1, so something in the 0.00 and then some values there, then what we're saying here is that the reactant side is favoured, so there's more reactants. If we get something close to 1, then we've got a similar amount of reactants and products. If we get a number much larger than 1, that means that our products are favoured. Alright, so let's take a look at each of these graphs and see what we can work out from them. So if we have a look here, we've got this graph going this way up. So the concentration of something is getting bigger. So we would suggest that this is our products forming. And in this case, the concentration of this is getting smaller. So we would say that this is our reactants being produced, being turned into products. So we can see here that the amount of products doesn't get to be the same as the amount of reactants. So our products is less than our reactants. In this case, if we have a look, our products are forming and they cross over here. So we end up with more products than reactants. So products are greater than reactants. Okay, this graph down here is not an equilibrium graph. We've only got one bit of information, so this doesn't tell us anything about equilibrium. And this one, our products are equal to our reactants. Alright, so let's have a go at our Kc values. So just a bit of a refresher. We know that this Kc value is approximately equal to 1. So let's just flick back and double check. So if we have more reactants, we're going to have a really small Kc value, so much less than 1. So let's go and fill that in. So our reactants were favoured in this graph. So our Kc value here is much less than 1. So on this side, our products were favoured, so our Kc value is much greater than 1. Right, the final thing for us to fill in on this graph is to have a look at where these are at equilibrium. So let's take a look at where the graph plateaus out, and we can see here that it starts to become flat in this area, so I would say our equilibrium is here. So this is where we are at equilibrium. And in this graph, it starts to flatten out about here, so this starts to become flat. So this is about where we've got equilibrium here. On this graph, it's about where they meet. So this is where we have equilibrium here.